Hello, my name is Kerem Kashkol. Today I'm going to solve you an example from linear algebra. Now, we are given a system like this. It's a simple system, a 2x2 system. We will first apply inverse matrix method and then reduction method to solve it. The system is actually quite easy to solve. You may apply old school method to solve it, but that's not the purpose right now. The idea, the rigorous way to solve it will be either of these methods, because consider like whether, let's say you have a larger example like 20 by 20 system, 20 equations in 20 unknowns. You cannot do it by hand. It's not really applicable. You need to have a better method. Inverse matrix method. Let's start with that. How do we apply it? We first need to write down the system in this form, AX equals B. And the way to do it will be as follows. Write down the coefficients matrix, 1, minus 1, 1, 1, the unknowns matrix, X and Y, and finally the constants on the right hand side, 2 and minus 1. The way to solve this question is as follows. First of all, A inverse must exist. Okay, given A, we must actually have A inverse. The unknowns matrix A, X, and the constants matrix B on the right hand side. Now, if we have A inverse, then we apply the following. Multiply both sides by A inverse to determine the result. Indeed, these cancel each other so that you have identity X, which is X itself, and on the right hand side, when you do the multiplication, you get A inverse B. So you obtain the result as X equals A inverse B once you have A inverse in your hand. This is actually how inverse matrix method works. The question is how to determine A inverse, and first of all, how do we know it exists? It's better to check out whether the inverse exists before starting to obtain it, before trying to obtain it. Check out determinant. Determinant of A will be, I'm not going to cover in detail, but 2 by 2 matrices, it should be easy. Just multiply the entries in diagonal, the main diagonal, 1 and 1, and the remaining entries, minus 1 by 1. Subtract the second one from the first. To obtain a number, if this number is non-zero, then you have A inverse. Okay, this means that A inverse exists. The method to determine A inverse is as follows. You just attach the identity matrix right next to it and start reducing it. Once you obtain identity here, and if it's invertible, you should be able to obtain identity here. The identity at the beginning becomes A inverse. So let us apply this method. Write down the matrix 1, minus 1, 1 and 1, and attach the identity 2 by 2 identity right next to it and start reducing it. What's the operation that we apply at first? We may use this one to convert the one below to 0, minus row 1 added to row 2. We obtain the following. Minus 1 added to 1, here it's 0. Minus 1 is 1, it's a plus 1 with the minus at the beginning. So this will become 2. This will become minus 1. And this doesn't change anything, and the first row remains the same. Now we may divide the second row by 2 or multiply it by 1 over 2 to obtain the following. And first row is unchanged. And finally, using the second row, we may convert this minus 1 to 0. So row 2 must be directly added to row 1. So this is our next operation. You cannot see it, but it goes on like this. Row 2 added to row 1. Row 2 is unchanged. And if you add it to row 1, you obtain 0 here. That was the purpose of choosing this operation. And minus 1 over 2, that was a 1 here. Added to 1, it's plus 1 over 2. And this was 0. So 1 over 2 added to here, another 1 over 2. So that's it. This is indeed the inverse matrix. It's inverse of A. Now we may finalize the operations we have. The multiplication phase. X equals to A inverse B. Indeed, this is 1 over 2 times 1 over 2, 1 over 2 minus 1 over 2, 1 over 2 times the unknowns matrix on the right hand side. If we check it out, it's 2 and minus 1, the constants on the right hand side. 2 and minus 1. We obtain the following result. If you wish, you may use a separator to calculate the product. 1 over 2 times 2, it's 1. And here it's minus 1 over 2, 1 minus 1 over 2, it will be a 1 over 2. And similarly, if you apply the product to the second row, you get minus 3 over 2. So that's it. This is the end of method 1. This is how we solve it using inverse matrix methods. Now, part 2, reduction methods. Let me rewrite the system. X plus y equals minus 1. Given this system, we start all over. How do we solve it? Using reduction method. Now, here's how we do it. Just write down coefficients matrix. 1, minus 1, 1, and 1. And attach the constants matrix on the right hand side. This is A. And here we have B, the constants matrix. And we start reducing it. We will apply a similar set of operations. Again, to get rid of this 1, minus row 1 may be added to row 2. Row 1 remains the same, and row 2 becomes 0, 2, and we have a minus 3 here. And 1 over 2, row 2 may be applied. First row remains the same. We get this kind of a result. I'm going to fast forward a little bit. Similar operations. Row 2 added to row 1. We obtain this kind of a result. So that's it. That's how we solve using reduction method. Actually, it's quite easier and more generic to apply reduction method when compared to inverse matrix method. Inverse matrix method may have its own advantages, but unless otherwise specified, you may prefer reduction method. So this is the column for x, this is the column for y. 1 times x plus no y equals 1 over 2. This means that x equals 1 over 2 and y equals minus 3 over 2. And as you see, we get the same solution. It's just represented in vector form on the right hand side. Anyway, so this was a brief introduction. We have solved the question in 2 different ways. A quick comparison, or let me put it this way. The inverse matrix method only works for unique solution. Unique solution means we have a constant for x and another constant for y. Now, once again, the reduction method is more generic. We may apply it to other cases as well. We may have no solution and we may have infinitely many solutions. Now, what about them? When do we have no solution case and when do we have infinitely many solutions? In the case of inverse matrix method, we need to have a square matrix A, otherwise A inverse doesn't exist. A inverse is not defined for non-square matrices at all. However, there is no such condition for reduction method. How do we apply the other cases? Let me quickly show it over this example. I'm not going to go over in a formal way. Let's say we have a 0 here. I just altered the final matrix. It's no longer a unique solution. Let's say it's not like let's say, but it corresponds to 0 times x plus 0 times y, which is just 0 equals to some number on the right hand side, which is not true. It means that we have a contradiction, which means we have no solution. So whenever you have a contradiction like this, this is the case. And how about infinite many solutions? So let's alter the question one more time to find out some infinite many solutions. Let's say we have a 0 row at the end and we obtain something like this. Now here is the formula for infinite many solutions. We need to assign some parameters. If there is no parameter, there is no infinite many solutions. Now number of parameters is actually number of variables minus number of non-zero rows after reduction. In our case, indeed we have 2 variables and only 1 non-zero row after reduction. So we have 1 parameter. By convention, we choose the last variable as the parameter, so y equals r, where r may be any real number. And what about x? Write down the system, the equation that you obtain from the reduced matrix, x plus y equals 1 over 2. So x will be 1 over 2 minus I. We call y as I. Remember that. And that's it. This is indeed the family of infinite many solutions. Since you have infinite many choices for R, you may obtain infinitely many particular solutions from this. Let's say call R equals 0. If you choose R as 0, Y will be 0, X will be just 1 over 2. This gives you a particular solution. Once again, you may have infinite many particular solutions, and That's pretty much what we have. Thank you for listening.